All right, got several questions this morning, so we'll kind of start working our way through terms of naming. Can we go over how to use cis-trans RS notation and easy for alkanes and alkyl halides? All right, so cis-trans RS, easy. These are going to start showing up with the rings, and problem is cis-trans and easy kind of are limited application naming, but we do need to know them. So let me give you a few examples to work with here. So easy has to be used when you have three different groups on the ring specific. So three different groups bound to two different carbons. So if we just have two groups bound to two different carbons, so let's say we've got a methyl group here and a methyl group here. This is a situation where we can use cis-trans because we can either refer to the methyl groups, whether the cis, which means they're on the same side, or the trans are on opposite sides. If we have a methyl and an ethyl, we can still do this because we've got the hydrogens. And so when we say cis in this case, we're saying cis with regards to hydrogens. But the restriction to cis-trans is that you can only have two substituents on the ring, and at least, well, basically you just need to have two substituents on the rings to use cis-trans. The cis-trans here is supposed to refer to the two groups that are the same if they're both like methyl groups or ethyl groups are the same kind of branch, or alcohols to alcohols, the diol. The cis and trans can refer to the alcohols. Typically, though, it's a lot easier to think about the cis and trans referring to the two hydrogens attached to those carbons. Easy shows up when we don't have two things that are the same on the substituted carbons. So let's say we have a methyl group, an alcohol, and another ethyl group. So here there's actually four things attached to these carbons. We've got an alcohol, a methyl, an ethyl, and a hydrogen. This is where the EZ is going to be needed. So the cis-trans is the easiest. It doesn't require calculating priorities and assigning whether the priorities are the same on both sides. But it's also more limited because we have to have two groups that are the same on the two substituted carbons. The EZ is harder, but you can do the EZ here and do the EZ here, but you can't do the cis-trans here because we have four different groups. So the cis-trans here refers to the same group. So in this case, we have two hydrogens. That's our same group. Are the same group cis and trans? Because we don't have two same groups, we don't have two hydrogens, two methyls, two ethyls, two alcohols. We use the EZ priority rule. So on this carbon, we've got a methyl group. That's a carbon. That's an alcohol. That's number one priority. Hydrogen here is lowest priority, so that makes the ethyl group highest priority. Because our priority groups are on opposite sides of the ring, this would end up being an IntGAN, an E opposite notation. Now, all of these only work if you've got two substituted carbons. And they can be anywhere on the ring. So we can have them beside each other. We can have it go 1, 2, 1, 3, 1, 4, 1, 2, 1, 3, 1, 4. If we have multiple substitutions on the ring, this is when we're going to need to start doing the R and the S. And there's actually more cases out there too than what I'm about to show you. So if we have, in this case, two methyls and an ethyl, the cis-trans here is ambiguous. So because we have more than one substitution, we're not really specifying we're not specifying here which carbons are substituted because there's only two substituted carbons. Here we've got three and we don't have a spatial arrangement. So we definitely need R and S for that. But that said, when we get substitutions like this, unless it's meso, we need RS as well. So the reason why we can get away with meso complexes not needing the R and the S is that there is no stereoisomer there. So we don't have to specify which one is which. But let's say we have, so if this were the dimethyl group, we could say that this is cis 1,2-dimethyl cyclohexane without needing to specify which chirality you have because it's got the mirror plane down the center. Now, let's say we do the trans 1,2-dimethyl. Here's the problem. I'm going to need to erase these down here. Which transversion do you have? Do you have the transversion where this one's back and this one's up and this one's back, or where the number one carbon is back and this one's up? And so when you start getting these stereoisomers that their mirror images are not, when they're not meso, basically they do have an enantiomer, then you're going to have to do the cis trans plus the R and the S. And the same thing is going to be true for the E and Z. If we end up generating something that does in fact have stereocenters and it's not a meso complex, that's when we're going to start adding the R and S in front of it. So R and S will work every single time. And in fact, I think it becomes a little redundant with the cis and trans, but whatever. Sorry, it's early in the morning. So the R, we have to do the R and S if we have, R and S is what we have to do if we have more than one substitution. If we have just two substituents, we can do the cis and the trans. And then we need to tack on the R and the S here in the event that we end up generating non-meso complexes. So yes, cyclic compounds quickly get complicated despite being very simple molecules. But again, like that's why we're doing this. So questions 23 through 25 on the test 3 material. Okay, synthesis. So synthesis is actually a fantastic way to learn reactions, and this is why they synthesis starts showing up at the on this exam. So if you take a look at pages 13 and 14 and 15, these are all the possible reactions you know at this point. So you know PBr3, you know HCl, thionyl chloride, SOCl, you know tolsyl chloride, and you know the effect of HBr, you know acid catalyzed dehydration, more thionyl chloride, more elimination. And then on pages 16, 17, you start getting into solvent effects. So you begin to see like how adding HCl in one solvent versus the other drives S in 1 versus S in 2. And then on pages 18, we start seeing nucleophilic substitution. So specifically S in 1, S in 2 reactions. Now the one I want to draw a parallel to here before we start going through the synthesis problems. Is the first one on page 18. So we have an OH negative, and what's going to happen here, we're in THF. This is fairly non-polar. This is fairly low dielectric constant solvent. We're going to get substitution, and it's going to be, I thought I drew that wrong. It's going to be an SN2 mechanism. So this is going to go through, hit that carbon, break off that bromine, and you do need to learn how these arrows work. So what I'm doing is I'm taking a lone pair, and when I draw a lone pair to a carbon atom, I'm making a bond. When I draw a line from a bond to an atom, I'm making a lone pair. So what I end up doing here is getting an OH and a Br negative. Now, the H here doesn't do anything, it forms an alcohol. So actually this can be anything. This can be an R group. And this is an alkoxide. So an alkoxide is an alcohol that has lost its hydrogen. So if we look at the first, we look at page 23. Make sure I'm answering the question. So page 23, we've got this starting molecule. And you're asked to do this, and it says this can be done in one step and if you utilize the alcohol. And what we're going back to here is this parallel about nucleophilic substitution. So our product here is the ether. And it's a 6-membered ring, including the oxygen. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And there's your methyl group. So this chain here, this backbone, is this entire ring. So what we've done is a ring closing reaction. What we're trying to do is we're trying to make a ring out of this complex. So if we draw the parallel here, if we have an alkoxide, we have something with an O negative in it, it can undergo nucleophilic substitution. So if I just add sodium metal, the sodium metal will remove the hydrogen, give me the alkoxide, and then this will attack the chlorine carbon, displace the chlorine, and that's how I do that substitution. So again, it's kind of drawing this parallel back to the OH minus from the few pages back. If we can get an O negative, we can get a good nucleophile, and this nucleophile will push out the chlorine and give us a 6-membered ring. Page 24. Write out the major possible products for the following reaction. We have isopropoxide and isopropanol. There are a lot of good answers to this one. So we've got 2, 4, 6, 7. So the isopropoxide, isopropanol was written up there for 2 reasons. One, it was easier than drawing it, but 2 is to make sure you understand what isopropoxide is. Isopropoxide is isopropyl alcohol. That's lost a hydrogen. So it's another alkoxide. Now, the reason why we like doing the alkoxide in its own alcohol is so that this will exchange hydrogens with itself. We won't end up with a mixture of alkoxides. Ooh, it's not Cl. OH. Now, we have what we consider a non-productive reaction where we pull a hydrogen off and replace it. We're not going to get much of that because this is a secondary alcohol. But if you look at it, what it's really asking you is, this is a very good strong base. And it leans towards the bulkier end of the spectrum. So in principle, we can get elimination. So one option here is we eliminate the chloride. Another option is that we eliminate the alcohol. Although this alcohol is not going to really want to do that. We can get the double elimination. Also, this is a strong nucleophile. In principle, we can get substitution of the alcohol. So there are lots of different ways we could have this go about. And so based on the carbon-13 NMR, what was made, we've got a symmetric, we've got, ooh, I like this. So if you look at it, it has 2 areas of 2, 2, 1, and 2. So the 2, 2, 1, and 2 means that we have a total of 7 carbons in the molecule. So 1, 2, 3, 4, 5, 6, 7. And there's a symmetry. There's 2 that look the same, 2 that look the same, 2 that look the same, and 1 that's unique. So if we're looking for a molecule that has a mirror plane here, it's this one here. So our least shielded, this is going to be carbon peak 4. We're going to have 2 strongly d-shielded ones, peaks 1 and 2. And then your last peak 3 here is going to be the center methyl group. So your possibilities are single elimination, substitution, and then double elimination. Double elimination is apparently what was made for this particular problem, but you can also get a witch's brew here. So this alkoxide can also substitute off the alcohol. This is actually a synthesis we'll learn about in the semester, where we can get an ether, we can get the double ether. Although we haven't covered ethers, which is why I wouldn't expect you to know how to do this. But the point of this problem is, one, to get you to think about the characterization, think about the different types of reactions that can occur based on what you know, and then kind of getting into this, how would I prove it? In this case, we're using the carbon-13 NMR to prove it by looking for a molecule that's consistent. So for each of these, you would try to generate an NMR spectrum. This one here would have 1, 2, 3, 4, 5, 6, 7 carbon peaks. This would have 7 carbon peaks, 1, 2, 3, 4, 5, 6, 7. This would have more than 7 because we've got the isopropyl group now. This would have more than 7 because the isopropyl, and this would have 1, 2, 3, 4, 5, 6 peaks. So it doesn't work. And I don't have a page 25 on mine, so let me check the course website. Yeah, I only have 24 pages in mine. All right, so that was the first email I get. Characterization as well as cis-trans, RS, and easy notations for alkyl halides. All right, let's go to the other set of questions. Reactions of alkanes and their products and characterizations. Pages 26 and 27 from the test 2 packets. So this is going to kind of be review. Yes, the problem that got updated. Page 26 and page 27. So we've got this 1,2-dimethyl pentane, or I'm sorry, 2,3-dimethyl pentane. There's such thing. That's the other one. And we're not specifying chirality with this. And it tells you off the bat, like, here are the possibilities. So we know we got the monosubstituted product, but what we want to determine is what we have. And so you look at the 1H NMR spectrum, it says, okay, you got 5 peaks, 1, 2, 3, 4, 5, quartet, septet, singlet, triplet, doublet. And I tell students the easiest way to interpret 1H NMR products is look for singlets, because singlets are the easiest ones to see in the molecule. So a singlet is going to be formed by an isolated methyl group. And so if we have a singlet, we have to have a methyl group that doesn't have any adjacent hydrogens. So if we look at this one, we've got 2 carbons here that have isolated methyl groups. So these are each going to produce a singlet. If you look at this molecule, this is going to produce a singlet because it's isolated. There's no hydrogens on this carbon. This is not capable of producing a singlet. These 2 methyl groups have a hydrogen here. This methyl group has a hydrogen here. This methyl group has a hydrogen here. So off the bat, we can get rid of product 3 because there's no way we produce an NMR spectrum with a singlet in it in order to produce this spectrum. So the next thing is to look at the area. And if we look at the area, this singlet has an area of 3. So this would give an area of 6. This would give an area of 3. So off the bat, we can get rid of this one. And so simply by looking at the singlets alone, we've tweezed out that it has to be the second product. Now, a good thing to go through is kind of get into the practice of once you're pretty sure you know what it is, make sure you can interpret the other parts of the spectrum. So the singlet here is peak 3. We have an area of 1. So we've got 1 hydrogen here. So if you look at peak number 2, it's going to be a septet. That means it has to have 6 adjacent hydrogens. It does have 6 adjacent hydrogens in this case. And peak 5, it's a doublet. That makes sense. That's next to a hydrogen. So we can assign peak 5 to these 2. And then we've got a doublet and we've got a quartet and a triplet. So peaks 1 and 4. Your triplet has an area of 3. So it's going to be this terminal methyl group. And your quartet has an area of 2. These 2 hydrogens here. So it's going to be this peak here. Now the reason I say it's good for you to kind of get into the habit of going through and verifying. Let's say your NMR spectrum, for whatever reason when you did it, both would produce a singlet of area of 3. Okay, so the singlet's not going to be the one that gets you to the answer, but your singlet does help you eliminate ones that don't work. And so you start narrowing it down and start looking for more and more unique features. But by getting into this habit of going back through and just kind of verifying, you can figure out how these other peaks would fit into this molecule. It'll help you out when you hit situations where the singlets aren't a fast way to eliminate possibilities. All right, next one. Give the 3 most likely products of the double bromination of pentane. And from the carbon-13 NMR data, what product was formed? You can ignore stereochemistry because carbon-13 is not going to really see the stereochemistry for this linear molecule, especially with a double substitution. So if you look at pentane, we have primary, secondary, 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 primary, and these are all related by a mirror plane. So double substitution, off. If we do a single substitution, we expect to get a bromine here or a bromine here. The double substitution, we're likely to put it here, since this now becomes a tertiary carbon. Here, since this becomes a tertiary carbon. And so the last product here, if you're just having a bad day, you'll form the disubstituted with two bromines, not on the same carbon. So you're given the carbon 13 here, and you're told that you've got areas of 1, 2, and 2. That's 5 carbons. So you're only going to have 3 unique signals. What you're looking for in that case is a mirror plane. So we know this doesn't work because we've got 1, 2, 3, 4, 5 carbons. So that's gone. This is 1, 2, 3, 4, 5 carbons. This one's gone. If we look at this, there's a mirror plane down the center. So there's your 1, 2, and I shouldn't have written it that way. So there are your 2 that look the same, 2 that look the same, 1 that's by itself. So there's your area of 2, 2, and 1. And the peak assignments here are 1, 2, and 3. So again, this is going to build on what you expect the reaction to produce. Disubstituted, disubstituted, and this is disubstitute. This one's much less likely on the fact that when you do your first substitutions, you're going to end up creating tertiary carbons. Those are much more likely to create radicals. So you're probably going to get double substitutions on the same carbons first. This can happen, it's just not very likely. So with all of these, what you're going to see, particularly for the later problems, and these later problems are really good examples of like the last questions on the exams, is putting it all together. Not only can you tell me what you think is going to happen with these reactions, can you characterize the final material and figure out, of the likely candidates, which is the one that you isolated. So particularly with this case, there are 3. I asked you to find 3 just to kind of give you the practice with the 3, but these 2 are the most likely. How would you resolve these with a technique? So I could also give you 1H NMR. And with the 1H NMR, a singlet here would indicate this compound because this is the only one that produces a singlet, this isolated methyl group. This doesn't have any singlets. These 2 interact and these 2 interact. So with the 1H NMR, you could also characterize them as well. Now the carbon 13 NMR, not going to do you any good because the the mass spec isn't going to do you any good because these both weigh the same. The IR is not going to do you any good because it's really hard to resolve alkyl halides with the IR. You get slightly shifted bending modes, but honestly, unless you're working with the fingerprint region, there's not much that these 2 can tell you from IR. But that's the thing. The goal here is to see not only, I'll start applying all this information. Can you predict what the reaction is going to make, or what would be a reasonable product? And then based on the structures of the reasonable product, can you apply some type of characterization? So you're given characterization data, can you isolate the one that you think you made? And again, as I told you when we started doing NMR, no one ever approaches NMR from scratch. Nobody looks at the NMR and goes, oh, this is this molecule, except for very trivial cases. So particularly with NMR and mass spec, you need some starting point. And that's what you're doing by predicting these reactions, is giving yourself a starting point. What are the possibilities here? And then based on those possibilities, which one is consistent with the spectrum? So that's it for the questions I've been asked. Again, these aren't lessons, these aren't lectures. These are 100% office hours, so I've got the chat up. If you've got questions, please feel free to ask. Otherwise, I'm going to basically just be here getting work done. right, so that's it for questions today. Again, if you have questions, please feel free to email them in advance or ask them in the chat. And I will see you all tomorrow.